Hey there and welcome to another LeetCode problem. So today we're going to be doing problem number 295, find median from data stream. It's definitely a popular problem. I think it might actually be on the top 75. I'm not really sure about that, but let's get into it. So the median is the middle value in an unordered integer list. If the size of the list is even, there is no middle value, and the median is the median of two middle values. So that's pretty straightforward. They just show how to calculate the median. So if you have an odd number of values, then the median is the middle value. And if you have an even number, then the median is the average of the two middle values. And so we have three methods we need to write. We need to write a median finder that initializes. We need to have an add num that adds from the data stream into the data structure. And we need a find median that returns a median of the elements so far. Answers within 10 to the negative fifth of the actual answer will be accepted. Okay, we have some examples, so just look at it real quick. So we add 1, we add 2, we get the median. The median, since there's two numbers, it's going to be the average, so 1.5 here. We add 3, and then the median is the middle number here because we have an odd number. Okay, so let's just think of some ways we can do this, right? First of all, there's a really straightforward way where you just have an array. And as you're adding numbers, you just figure out where to add that into the sort. So we have sorted array, and we can add numbers in. We can do that one of two ways. We can just append and sort every time, or we can just loop through the array and figure out the index of where to put it. We can actually insert a number in an array with log n time technically, but let's say we have, n numbers, and to insert, we can do log n because of binary search, right? It would be n log n here to add n numbers. And can we do better? Can we add numbers quicker? And can we get the median quicker? Well, what do we really need for the median? So for the median, we need to know how many numbers are in our array, which is pretty straightforward, right? We can just have some variable there. And we need to know the middle number or the middle two numbers, right? So if we have something like this, if we know that there's an odd number, as long as we know what the middle number is, or the middle, let's say we have the middle or the middle two, right? One or the other. Then we can get what it is. Well, what if we do something like this? Instead of knowing the middle number or the middle two, what if we can split our array into two parts? So we have a left and a right part. And let's just say, so we're going to have a couple scenarios. Let's just say that these lengths are roughly equal. One can be bigger than the other, or they can be the same, right? And so when we have something like this, and obviously they're going to be the same. So we have a left and a right part, and obviously they're going to be the same. And if they are like this, then we can either have something like this, like this, and it doesn't really matter too much. We can figure out the median really fast. We can just take the length of either one, and whichever one has a bigger length, we know where the number is in the median, right? So if it's a bigger, or let's say it's an array for now, then it's going to be the element on the left, and if the bigger one is this one to the left, then it's going to be the element on the right. Well, that's okay, but the thing is, we don't really want to have arrays. What we really want is another data structure that we can split our elements in half, or close to half, right? We either have them equal or one off. And then we want to know the smallest or biggest element in that data structure. And so what data structure do we know that lets us do that? So we can split our data in half, and then we can, all we really need to know is the biggest or smallest element, right? So for this smaller one, we need to know the biggest element, and for this bigger one, we need to know the smallest element. Well, we can actually use a heap for that, right? That's what a heap does. And so let's say we have these numbers like this, 1, 2, 3. Well, what if we have these numbers 1, 2 in a heap, and then 3 in a heap? And obviously in Python, there's only a min heap. So for these small numbers, in order to get a max, we would store them in a negative way. So we'd store it like this. Then we can get a min really fast. We could just get this. And for this right side, we would store the numbers positively, and then we can get the min right away as well. And then we can easily figure out the length of both of them. So we can try to make sure that the length of both of them is, like I said, either equal or one is one off from the other. And if we know one is one off from the other, then we know exactly where our number is, right? Because if this one's longer, then this is going to be the middle number. And if this one's longer, then this is going to be the middle number. Okay, and if they are the same, right, so let's say we store something like this, then we just take the min here and the min here, and we take the average. So now that we know roughly what we're going to be doing, what is that going to look like with our additions and our insertions? And so what we can do is, like, let's just go through this 1, 2, 3. So we're going to have a heap over here and a heap over here. And it's going to be the way we're going to separate these heaps is the biggest element in here. So let's just call this heap 1. So max of 1 has to be, I believe, do we get new? No, max of 1 has to be less than or equal to min of 2. And that's what we want our heaps to be ideally. And so for originally, whenever the length is equal, actually we don't even need to know if the length is equal. What we actually need to do is we need to say, let's say for a base case, we can put our elements in whichever side, right? So our base case is when both heaps are empty. So let's just try these numbers like in some weird order, like 5, 2, 3, 6, 1, 4 maybe. And let's see what that would look like. Okay, so we'll just say that when both heaps are empty, we'll just put in our element in the left, or yeah, sure, the left heap, right? Okay, now what we need to do is we need to go through one, so we put that element in there. Now let's just see how we would get these other elements and how we would put them, and then how would we, remember, we have to have the length of both of these heaps either equal, or one has to be one more or smaller than the other. Okay, so let's see what that would look like. So let's say we have this number 2. Well, where can we put this 2? Well, like I said, the biggest element here, right, has to be smaller than the smallest element here. And so the biggest element here is 5. So we can't put the 2 over here, right? Because 2 would be greater than 5. And so that wouldn't work. So we'd have to put the 2 over here. Now what we have to do is every time we put something in, we have to restructure the heap. So like I said, our heaps are equal in size or they're 1 off. And here the length is 2, and here the length is 0. So what we need to do is we need to say, while the length of one of them is too big compared to the other, we need to pop from one and push to the other. So what does it make sense to pop? Well, we're going to want to pop the biggest value here, right? And these are going to be stored negative, remember? So we can just pop the biggest value by actually having them stored negatively and popping this. This is going to be the smallest value in a heap, but it's going to be the biggest value, right? So we can just pop this -5 multiplied by -1. Then we push it over here. So now we have a 5 here. This goes away. Okay, we got rid of this 2. And now the heaps are balanced. So let's just go to the next stage where we have -2. Or sorry, this would not be a -5. This would be, yeah, this would be a 5. And then here we'd store a -2. Okay, so now we try to put a 3 in. Right, so where would a 3 go? Well, a 3 can technically go in either one, right? If we put a 3 here, it would still match that the biggest element in here is going to be smaller than the smallest element. But so we can put the 3 in here or in here. Let's just say, for simplicity's sake, we're just going to put, whenever we have a choice, we'll just put things in the left heap. So we're going to put a -3 in here, right? And we still have our matching that the biggest element in here is smaller than the smallest element in here. That's true. And now these heaps are only off by 1, so we don't have to do any kind of restructuring. And notice how if we ever needed to get the mean, we could, or the median, we could easily do it, right? So for this -2, 5, we could easily just get these two values and get the average. For this, we know that the length of this left one is bigger, so then the median is going to be the value that we care about in this heap, which is going to be this value. Now let's try to put in 6. Well, where can we put in 6? Well, we can't put in 6 on the left, right? Because it's not smaller than 5, so we'd have to put 6 in here. And so once again, these heaps are still balanced, so we don't have to do any kind of restructuring. And then 4 would have to go on the left heap, right? Because remember, the biggest element in the one on the left has to be smaller than the largest element. Or sorry, than the smallest element on the right. So we'll put 4 here. Now, the this heap is length 3 and this heap is length 2, which is still fine, right? They're okay to be one off. And so that's kind of what our algorithm is going to look like. Actually, sorry, no, these heaps are the same length. So no, I'm just kidding. So these heaps are the same length. And once again, the median, really easy. We just take the two middle values if we need to and get the average. So that's going to be kind of how our algorithm is going to look like, is we're going to put stuff in the heap, and then we are going to restructure them at the end of every addition to make sure that they're roughly equal size. And then we can easily get the median by just figuring out if they're equal length, then it's going to be the average of these two. And if they are not, then it's going to be the min value of the longer heap. So hopefully that makes sense, and let's try to code that up. Okay, so first we're going to have two heaps, right? So we'll just call this left heap, right heap. And we're going to need two self. Okay, so let's have a base case. And our base case is if they're both none. So if not self dot left heap and not self dot right heap, then we're just going to put into our left. Pretty straightforward. So self dot left heap. We don't even really need a heap push. We can just do this because there's only one element, so there's nothing to sort. Okay, so that's one case. Next case is if the number is, so actually let's think about this. Okay, so actually instead of doing this if not left and right, yeah, so instead of doing this if not left and right, let's just say if there is no right heap, let's just push into the left. Okay, that's more straightforward. And then we would have to, and then we can restructure later, right? So if there's no right, let's just push onto the left because we don't have that criteria of we need to be smaller than we need to be smaller than the smallest element in the right heap. So if it's not here, let's just actually heap push self.left heap, and then we'll restructure later. Left heap. And remember, this actually needs to be negative num. I forgot. Okay. Now let's say if they're, so we can never have the case of, because we're never removing numbers, so we can never have the case of we have a right heap and not a left heap. That's not possible. So we either have two heaps or we're going to have a left heap. And so if we have two heaps, then that's going to be our else case. And now we're just going to push to the heap that it needs to go, right? So if num is a less than, and that's going to be self.right heap 0. So if num is less than the smallest number in the right heap, then we push it to the left, right? So let's heap push self.left heap, remember negative. Else we push it to the right heap. And this is going to be positive. Okay, so now that we pushed our numbers, now what we need to do is we need to restructure, remember? So we're going to say while length self.left heap, let's say. So let's restructure this first. Is less than or equal to, is less than or equal to self.right heap. Oh, this is length. And then this is, so let's think. So they have to be more than one off, right? So I think it's actually like this. So that means they're more than one off. Because like if this is 1 and this is 2, that would be fine. But if this was 1 and this is 3, it wouldn't be fine. I think it's actually not less than. I think it's just less. Sorry, it's not less than. It's less than. This is saying while the left heap is 2 or more smaller than the right heap, then we need to restructure. So let's restructure. Pretty straightforward. So the way to restructure, remember, is if we want to move from the right to the left, we're going to take the smallest number in the right and we're going to put it in the left. And that way we're still going to maintain this biggest number in the left is less than or equal to smallest number in the right. Okay, so let's do that. So let's just say we're going to have num or something equals heap pop self.right heap. Okay, now we're going to heap push that to the left heap. And remember, we're pushing in a negative number, so negative num. Okay, so that'll take care of the case where the left is smaller. Now let's take care of the case where the right is smaller. And so that's going to be, we can just reverse these two. So right +1, left. Okay, so now we are saying that the right heap is 2 or more smaller than the left. And so we are going to push pop from the, sorry, we're going to pop from the left. Left heap. Okay. And now we're going to push onto the right heap. And remember, this num we popped off is negative, so now we need to make it positive by doing this negative num. Okay, so that should be it for the add num, which is the complicated part of the code. So now these heaps are guaranteed to be, right, like if we pop from the left, like let's say it's -2, -3, -4, the value we want to push to the right would be this -4, right? We always want to push the negative value from the left to the right, or the smallest value from the right to the left. Okay, so now that we're guaranteed that the length of these is within 1, now it's pretty straightforward. So now let's think of what things we could have. So if length of self.right heap, left heap, let's say, equals length self.right heap. So if they're equal length, what we need to do is we need to get, remember, and I think, yeah, so there will be at least one element of the data structure before calling find median, so we don't have to worry about them being empty. So if they are equal, that means there is an element in both of them, and that means we just need to get the rightmost element from the leftmost element from the right, and take the average, right? If they're equal, that means there's an even number. So let's just do return, or let's just do num1 and 2 equals heap pop self dot left heap, right? And it's going to be negative, so we need to make it positive. Okay, and then the other number is going to be heap pop self right heap. Actually, sorry, so this is a mistake. So we don't need to do a heap pop, right? We're not popping, we are just getting the value. And so actually this is self.left heap. It's going to be -1. Just do this. So remember, to get the top value in the heap, you just do heap 0. We aren't actually popping them, we just need the values. And then the other one is going to be self.right heap 0. Now we just return num1 plus num2 over 2. So we just that in parens, and that'll give us the average. So that's one case. Now another case is if the length of the left is greater than the right? In which case, so if the length of the left is greater than the right, then we're just going to be returning the element on the right there on the left, right? So if it's like -2, -3, 4, 5, 6, then the element we want would be this -4. So that's pretty straightforward. So return negative self.left heap 0. And just do this just to make it more clarified, but I think just negative would work as well. Okay, and then the last case is that the right side is bigger, so then pretty straightforward, return self.heap. Okay, let's try that. Okay. All right, cool. See if that worked. Yep, nice. Okay. Okay, so let's think about the time and space complexity here. So I think for the time, so our init will be O1. Our add num will take big O of log n because we have a heap push, and then our median is going to be big O 1 time. So the thing is, if you did have a sorted array here, it would also take big O of log n time to find where to insert. But then if you're inserting in the middle of a big array, that's going to be big O of n time because you might have to shift the elements. So the nice thing about a heap compared to inserting into arrays, we are saving time because this is log n to heap push and heap pop, while inserting in the middle of an array is big O of log n, or big O of n. So that's what we'd be saving. So for each add operation is log n, and then for each of these is big O of 1. Okay, and it's a space. The space worst case scenario, we are holding every single number that we added, whatever that is, however many numbers we added. So that's going to be big O of n. Okay, so hopefully you understand why a heap is faster than inserting into the middle of, even if it's a sorted array, you're still inserting to the middle. And so this is the optimal solution here. All right, and so this is it for this problem. And if you like this problem, please like and subscribe to the channel. It really helps us grow it. And I'll see you in the next problem.